Hi, this is Ms. Fitzmaurice, and this video is an explanation of problem 76 in chapter 12 of Giancoli. So before you watch this video, make sure you try to do this problem by yourself and then check back for the answer. Alright, so in this problem it says that we have a tuning fork, okay, and that's a little vibrating fork that makes a sound at a certain frequency. And the problem tells us that the water level in this tube, so this tuning fork is held over a tube of water, and the water level is raised and lowered. So you hear something first when the water is 0.125 meters from the top, and then again when the water is 0.9395 meters. Okay. And so what we want to know is what is the frequency of the tuning fork. So the strategy we're going to take is we're going to use this idea that V equals lambda F. Okay. Because it doesn't say not to, we can assume that the speed of sound is about 340 meters per second. Okay, that's pretty much always going to be true unless they say assume it's not true. And so that's going to be equal to the wavelength times our frequency. And so what we have to do is we have to use this picture to figure out the wavelength. Okay, and you might be saying, well, this thing is open on one end and closed on another, so I'm going to draw my harmonic waves so that I have one node and one antinode. The problem with that is that water is not quite like running into a solid object, and so we're going to have high pressure built up by the water, so that's like a node, but not quite. There might be something like extra inside of the water, because some of the sound will go into the water, and we'll have definitely a node, so I'm not drawing this very well. We'll definitely have a node or a low point in the pressure at the top of the glass. So we definitely have a node at the top of the glass, and then maybe we have a lot of pressure here, but maybe some of the pressure went into the water, we don't really know. Okay, and then for the second harmonic, again we're going to have a node at the top of the glass. And then something's going to be happening, we don't quite know what, at the surface of the water. So we definitely have a node here. Okay, and then we know we want to end on something like an antinode, but we're not really sure. But we can probably guess that the pattern should be kind of almost the same as it was last time. Okay, so what we can do is we can realize that the difference between the two water levels, okay, so the difference between here and right here should be a full loop or a full half wave. And so what we can do is we can say that the difference between my two water levels, 0.395 minus 0.125, is equal to lambda over 2. And so my wavelength is actually going to be 0.54 meters. Okay, so I can take this and put it up here for lambda. I have 340 is equal to 0.54 meters times f. I can solve for f, and I get f is equal to about 630 hertz. Okay, so again, what I did is I used my wave speed equation, and then I had to use the picture to find my wavelength. I solved for my wavelength, I put it back into the wave speed equation to find frequency at the end. Okay, and if you weren't convinced by my really crappy picture from before, here's another picture. So let's say that this is our first harmonic, and we don't know what effect the water has, but we do know that it's going to be kind of like something that is closed at one end and open at the other. Let's say it goes a little bit past the antinode, so here's our antinode. Then for the second harmonic, we're going to have the same type of interaction with the water surface. So we're going to be, let's say we got down this much extra from the antinode. We're going to be down that much more from the antinode again. Okay, and then if I drew a dotted line, hopefully you can kind of see that this section, if I moved it down here, would be equal to a full half wave, because it's a full loop, so it's half of our wavelength.